Thank you very much. I apologize for not introducing myself earlier. I'm Susan Solomon. I've done a lot of research in climate change and ozone depletion. I was the co-chair of Working Group 1 of IPCC in 2007. And I'm going to talk about practical mitigation. I think we're all aware that our climate has changed dramatically, and if you show people a figure like this, it's just so amazing how pervasive the warming has been over the last 50 years compared to earlier. What that means is that the average temperature, say in the summertime, will have become a little bit hotter. And while that change of a degree or so may not be as immediately apparent to everyone, what is apparent is the change in the extreme hot summers. So if you look at the distribution of summers anywhere in the world, you'll typically see a bell-shaped curve like the ones I have there. And this is sort of the classic cartoon that if you move it over a little bit, you get a less cold summers, say, but a more record hot weather. And you can even take it outside the range of what it's ever been. This is a very important figure, I think. It's the shifting distribution of summer temperatures, where summer is defined as the 3 warmest months over the northern hemisphere. And you can see how dramatically it has shifted to the right, meaning that we are getting summers now in some places which are much, much hotter, routinely hotter than they used to be. There'll be another decade on there very soon, and it'll be a very dramatic one, I'm sure. So when we think about this, it's useful to try to bring it back to the local level. And since I'm from the Boston area, I often show this image. It's just the days per year over 90 degrees Fahrenheit or 30 degrees Celsius. And you can see what our future is if we keep putting carbon into our atmosphere as we have been doing. It will become a very, very different Boston. And of course, the impacts are not limited to temperature. We also have to be aware that sea level rise is a major problem for many communities, and we already have parts of the world that have basically been slated, if you will, as sad as this sounds, to end up being underwater in the next few centuries, if not less than that. So record temperatures are very impressive, and they help us to understand what I like to refer to as the 3 Ps of addressing any environmental challenge. Is it clearly perceptible to people? When you have a record temperature that we've never seen before, it becomes perceptible. Is it personal? Certainly it is, more so if you don't have air conditioning or if you have to spend a lot of time outside, if you labor outside. And are the solutions practical? And the myth that's been sold to us for a long time is that the solutions are too expensive. They're impractical. And I'm going to show you that is no longer true. In any case, the situation that we're facing demands a careful look not only at practical mitigation, but also at resilience, the extent to which different places are able to deal with the climates that they are being increasingly dealt. So one way to look at this is to think about summer temperatures. Summer is a good choice because, of course, it's the hottest time of year, but it's also a less variable time of year typically, so it gives you a sense of where things are going outside the range of the past. And so this is just showing you on the left models of the temperature change for the last decade of the 20th century compared to the whole century. So the model is on the left, the observations are on the right, and you can see how dramatically temperatures have risen over basically all the continents. But contrary to what people's intuition might be, that the place where the signal to noise might be the most obvious you might think be the Arctic, because that's where there are big signals. The thing is that the variability is also high in the Arctic. So you can look at that, and you can put the two together and think about signal to noise. And there's a lot of papers that have done this over the past 10 years, roughly, and they all come up with the same thing, which is that the regions where the signal-to-noise is emerging the most clearly are in low latitudes, outside of the El Nino region. The El Nino gives you high variability in a limited region, but everywhere else, what you see is a tremendous change in signal-to-noise. So I would argue that the low-latitude countries are on the front lines of resilience, on the front lines of global warming, just from purely a physical science point of view. You pick out points around the world, you can see how different summers are already happening now. They're outside the range of past variability, therefore outside the range of natural resiliency. Different summers are coming in the future to higher latitudes, but for the moment, the extremes are within the range of the past. So people are already, they have developed resilience to that level of extreme, even if it's happening more often than it used to. But when things get completely different, all bets are off. Effects on crops, forests, ecosystems, people, economies, all those things are become in question, and things will begin, and already are, emerging in ways that we had not anticipated. Joachim already showed this. This is from a very nice paper on the changes in deadly heat waves. If you think about again, the distribution of those, you'll see a resemblance to what I just showed you. It's worse in the humid low latitude regions. That's because of the fact that these places are already hot, and the humidity has to do with the ability of an organism to cool itself literally by sweating. So if you are in low latitudes, in wet environments, humid environments, that's going to become much more difficult. And of course, we had the terrible example of the Indian heat wave recently, which killed quite a few people. So you can see where that is going to become more and more extreme, but it's already extreme. So lots of different greenhouse gases are changing our climate. We all know this, but CO2 is the major driver, and it's only CO2 that's embedded throughout the global economy. It also has another very scary feature, which is its incredibly long tail of lifetime. What this is are some figures showing you model calculations. This was first done around the late 00s, where people would run these Earth models of intermediate complexity and take a look at what would happen as you drive the carbon up to higher and higher levels, 350, 450, 550, 1200, et cetera. And then just go cold turkey, just stop emitting. And you see that long decline. And even by the year 3000, you still haven't gotten back to the baseline. And the reason for that has to do with the fact that eventually the sink for carbon lies in the deep ocean and becomes essentially a process determined by weathering of rock. And so that's going to take a very long time. You might imagine that the temperature on the planet's surface would follow the CO2 change. I always did. That is not correct. If you look at the corresponding temperatures, there they are. And for whatever value of CO2 you rise to, you have essentially a constant temperature to within plus or minus half a degree for at least 1,000 years. So I, at that point, said, hey, we have to start thinking of these things as irreversible unless there's some kind of engineered solution, geoengineering, which we don't have in hand right now, and I think it would be obviously very risky to count on it. Basically, what that's telling you is that the system has a massive lock-in so that what we produce will be with us in terms of warming, in terms of changes in rainfall, all those things. Sea level, by the way, will continue to rise. And the reason that you see that leveling off is because although CO2 is dropping, the rate at which heat is taken up into the ocean is also dropping. And the two things more or less compensate for each other. I wrote a paper in 2010 in PNAS that talks about that in more detail. Methane, by the way, while it also, while it has a 10-year lifetime also, actually, its effect lasts longer than you might think. So methane is an important greenhouse gas, but it's not as important as CO2. And this is really the basis for understanding that cumulative carbon is what controls warming. And the sea level rise continues for millennia because the ocean is still taking up heat. Resiliency, therefore, is urgently required. Yeah, I think I'll skip that one. So this is from the IPCC Working Group 3 recent summary, and we've already talked about it, so I won't spend much time on it. To avoid 1.5 or 2 degrees C requires unprecedented emissions reduction starting essentially now. And we've already basically overshot the 1.5 value. So will we allow overshoots? Will we allow it to get to 1.5 and then come down, or much higher values and then come down? That hasn't actually been answered by the parties, and I think it needs to be addressed. A big reason that we're in so much trouble is not just what we emit today, but the commitments to more future emissions from all the stuff that we have installed. So it's all the things that currently exist that rely on fossil fuels that we plan to use for 10 years, 50 years, maybe even longer, implies not only the physical lock-in that the system has, the climate system that I already talked about, this is the human lock-in. And there's a recent paper by Trout et al. That shows very nicely that we've already locked into more than 1.5 degrees unless we retire things like power plants very early, which of course companies don't want to do because they've invested a lot of money in them. Retire offshore oil platforms, get rid of the use of coal. Well, the coal companies, you can see that little tiny human being there, they own these massive assets, and their business is about extracting their mineral rights. So there's trillions of dollars locked up in that coal seam, for example. Can they change is a serious problem. They need to change. Why should they change, or why should we make them change? Well, energy, non-fossil energy has gotten vastly cheaper over about the last 10 years. This is for the United States, but other countries are similar. If you look at the cost of solar and wind, it has dropped well below the cost of coal, and that change from 2009 to 2015 is just astonishing. Economies of scale and global innovation and policies, and I want to mention in particular, I guess, the European leadership of the Kyoto Protocol led to a massive investment, which helped tremendously to drive these economies. Technologies, Obama-era research money, and that's continuing. Tax incentives, all those things contribute and drive the reduced cost. So they're now cheaper than coal, and they're even cheaper than gas for onshore wind. So all those, what it means is that if you're going to build a power plant today in the United States, you won't want to build a gas plant or a coal plant unless you're relying on it to solve the intermittency problem, which of course is important, but is not something that we need to dwell on until we get to higher levels of non-fossil energy. And I think Rob Stoner may talk about that. So what is practical has changed incredibly quickly, and the IPCC report of this year really gives us a tremendous amount of hope. This is the same kind of curve. It's hard to read, but it's showing you the same quantities on a global scale. And basically everywhere, non-fossil energy has become extremely viable. Batteries have also become extremely viable. And what that also means is a democratization, as I mentioned earlier, of energy. You don't have to, every little town can have its own power plant. You don't necessarily have to be looking at a large-scale plant that, takes control away from local people. So I want to play the blame game a little bit, talk about the human side of climate change. And here I'm going to just show you some figures on the carbon dioxide emission in tons per person per year. Different countries are shown there. That's the United States, us meaning me and a number of other people in this room. Why we do it, energy, transportation, industry, household, service sector. If you look at this kind of plot, you see countries near the bottom, and all we usually say is, well, they just don't emit very much. But it's useful, I think, to turn this on its head and ask the question of what the ratio of US per capita emission is to the country of interest. And you can see that the average American emits about 150 times more than the average Ethiopian or Chadian or Congolese. That to me is a very sobering number. I mean, it means that I, as an American, emit about the same amount as a village does, just me by myself. That's pretty shameful. And of course, if you're European, you know that you emit about half as much as we do, so that helps, but doesn't help enough, because lifestyles that we currently have indeed are not sustainable. On average, 6 billion people in the developing world today emit about 4 times less fossil carbon per person than the other 1.5 billion who are mainly in the developed world. So as those people develop, if they use carbon the way we did, the planet's going to get very hot indeed. So what is ethical and fair is a very important side of this discussion. If you look at the global pathway for 2C, and you ask the question, how much of the cumulative carbon budget have we already used up, and what's left? You know, when we first started this discussion, it didn't look nearly as bad as it has become. And the amount left for the rest of the world has become, I guess I'll stop 2020 there, is already becoming shamefully small, and if we keep going as we are, is going to be completely impossible to make the transition practical. So what needs to happen is an accelerated transition away from fossil energy. Faster reductions are urgent in the US, Europe, and China, and of course, financial support and mechanisms from developed to developing countries are also essential in order to make this all work. So the IPCC produced this remarkable but somewhat unreadable table. The only thing I want to emphasize is if you look at the top 2 lines there, everything that's blue, by the way, are things that are no net cost between now and 2040, I believe. Actually, maybe Joachim can correct me on that if I'm wrong. Look at how blue and how big the first 2 lines are. That is the wind and solar. Those are the wind and solar pieces. So that's where a lot of the cheap and achievable gains are to be had. What is practical, though, depends not just on cost and on science, but on human values. Still, I think it's universally a value that things that are low cost or no or very little net cost are things that everyone should support. So what's critical now is the rapid deployment of wind and solar. I don't think we need to dwell on deep decarbonization. I hope we don't have those words in the report, actually, because it's so easy to become distracted by the idea that it's almost impossible to get to zero now. You know, that's not the question. The question is, what can we achieve now? And we can go a long way in the next decade. By the time that decade is over, we'll know much better what to do about aviation and other things, just as we have every decade in the past. So certainly efficient buildings, lighting, appliances, and equipment are in there, and they are also low cost. Electrified and efficient transportation is again another low cost item. Avoiding methane emissions in fossil fuel extraction and in waste is another low-cost item. Reducing fluorinated gases is already happening, I'm proud to say, under the Montreal Protocol, with a lot of support from Pope Francis, actually. And reducing deforestation is another item that clearly belongs in this list. So I think it's not useful to think about ways to reinvent this curve, or this table rather. So much effort went into it, and in fact, it's a very nice construct for thinking about what we actually can do now and the urgency of doing all of those things in order to have a world that is both more just and frankly that avoids catastrophic problems of unknown scale. And that's all I had to say. Thank you.